Okay, right over here you can see a practice problem. You can try this solve this practice problem like we had solved the previous 2D truss practice problem using the stiffness matrix or the direct stiffness method. Right, you can do that, but as you have seen that method is a lot time consuming method. I mean, I had the slides prepared, so it was easy for me to explain it, but if you were to go to do that by hand and writing on a piece of paper, then it's going to take a lot of time for you, a lot of calculations, and this can be a lot painstaking. So that is where the computer programs or the softwares come in and help you with the direct stiffness analysis, the finite element analysis. So let's say that if you don't have access to a computer or a software or to the programming language, all you have is a pen, paper, and a scientific calculator. So in that case, how can you apply the direct stiffness method with ease for a 2D truss? So what you can do is you can try to figure out what the zero force members are. So once you figure out the zero force members, you do not need to analyze for those members because those are zero force members. The members that are not zero force members will be your concern. In that way, you can lessen up a lot of your calculations. Okay, so that is what we're going to see here. So we have a truss here, we have a 2D truss problem right over here, and what we're going to do is we're going to opt out these zero force members. So remember from the previous lecture, we have discussed the short notes on how to identify a zero force member. So here this node, the H node, doesn't have any hinges on it, any supports on it, neither does it has any loads on it. So the adjoining two members are going to be zero force members. So this is a zero force member, this is also a zero force member. Similarly, the joint A right over here, if you consider the joint A, then if you consider the joint A, then B and G right over there, then you can see that this particular member is also a zero force member. There you go. If that's a zero force member and there is no loads or nothing right over here, so the AB is also going to be a zero force member. And now you can see that the member GB or BG, whatever you want to call it, this member is has two supports at both of its ends, and from what we have learned or seen, that this can be considered a zero force member because it has two supports at both of its ends. So that is a zero force member. The similar case is happening in BC, two supports at both ends. So this is a zero force member, and similar case is happening with CD or DC, whatever you want to call it. So this is also a zero force member. Similarly, if we look at joint E, we can see that there are no supports nor loads on it. So the ED is a zero force member and the EF is also a zero force member. So now that we have identified the zero force members, we are left with a truss like this. This is the truss that we are left with. There you go, there is a support there. There are three supports here, here, and here. This is F, this is G, this is C, this is B, this is C, this is D. So this is the truss that we have to solve for. Since all of the other members are zero force members, we can consider them to be zero force members, and then we can solve for members till, let's see, 1, 2, 3, 4 members only. So this will make our work easier because we have to write equations for 4 members only instead of all these members. We can just write the equation for 4 members. Okay, so that is one helpful thing. So what you can do now is you can just do a practice for yourself and try to solve this using the stiffness matrix, and we have already discussed one example, so you know how to do it. So you can try to do it yourself, and in the next video we're going to see something very interesting as well. Okay, that was it for this video. Thank you very much for watching.